By now, you've surely picked up on the idea that the study of natural history is basically the study of how the world has changed. The study of how we all got here. And of course, the world continues to change all the time. I mean, literally. I'm not just talking about how life adapts or how the climate is changing. I mean, the planet itself as an object is in a constant state of flux because the ground beneath your feet is always moving. So the place where you are right now was not always there. For example, if you're watching me in California right now, then about 500 million years ago, the place that you currently think of as here was actually on the equator. And it was underwater. Likewise, if you're in the UK, then your here was almost at the South Pole, and your next door neighbor was Africa. We know all of this thanks to Paleo Geography, the study of how the physical face of Earth has transformed over time. And it's this movement of the continents that has driven many of the major revolutions in life's history. Its advances and its setbacks, its explosions of life and its extinction events. So if natural history is the study of how we got here, then you also have to understand how here got here. If you want to know how your here got to be where it is, you first have to know where land comes from and how it behaves. And for a long time, we just didn't know. The idea that the continents could actually move was first proposed in 1912 by German scientist Alfred Wegener. He spent years traveling the world collecting geological and fossil evidence to argue that all of the continents were once connected. Wegener was the first to propose the idea of continental drift, and the notion was so outlandish at the time that it basically cost him his career. And part of why no one accepted Wegener's theory was that no one in his day had ever seen the bottom of the ocean. Until the mid-20th century, most scientists assumed that the seafloor was basically featureless, like a giant wading pool. But in the 1950s and 60s, pioneering researchers like Marie Tharp and Bruce Heezen began studying the bottom of the ocean. And they found that there was an enormous mountain range running right through the middle of the Atlantic. Eventually, more of these undersea mountain ranges, called mid-ocean ridges, were found in all the world's oceans, and they were all volcanically active. These ridges, it turned out, are where the seafloor is made. Geologists realized that these mid-ocean volcanoes are actively creating the rocky material of the seafloor and spreading it outward in a process called seafloor spreading. But what the sea gives, it also takes away. Far from these ridges, at the edges of continents, researchers also found huge trenches. And here, the dense rocks of the seafloor dive below the lighter rocks of the continents in a process called subduction. So the denser, heavier crust that makes up the seafloor, known as the oceanic crust, moves under the lighter land masses, known as the continental crust, just a few centimeters at a time. And as oceanic crust sinks back into Earth's interior, it begins to melt and mix with the mantle. So seafloor spreading and subduction are the two key mechanisms behind plate tectonics, the theory of how giant chunks of Earth's crust, called plates, move around the surface. And together they explain what Alfred Wegener never could. They show us how the continents of our planet come together and break apart. But Wegener was right. Throughout the planet's history, land masses have been joining together to form supercontinents, only to break up again millions of years later. Supercontinents begin to separate when the mantle that's turning around beneath them starts to change, like in direction or temperature or intensity. These kinds of changes, we think, can cause plates that were once pushed together to gradually spread apart. When plates separate, they first create a rift valley, like the Great Rift Valley in Africa. Then as they keep spreading apart, they can form narrow seas, which is how the Red Sea came to be. Eventually, these gaps can open up to become a whole new ocean. That's actually how the Atlantic Ocean formed. This whole process of continents coming together and splitting apart is known as the Supercontinent Cycle, and it is what has changed the face of the Earth over the eons. Now, you've probably heard of Pangaea, the landmass that contained almost all of Earth's dry land about 250 million years ago. For a long time, experts thought that was the world's first supercontinent. But today we know it wasn't the first, and it won't be the last. One of the earliest supercontinents that scientists have evidence for is called Knorland. It existed 2.7 to 2.5 billion years ago, toward the very end of the Archean eon. It was made of continental crust that would eventually become parts of North America and Africa. And even though we call it a supercontinent, Knorland actually wasn't much bigger than Australia is today. Life on Earth at the time of Knorland was probably mostly single-celled, like the photosynthetic cyanobacteria that were starting to add oxygen to the atmosphere. Then, 700 million years after Knorland spread apart, another supercontinent began to form, called Nuna, or Columbia, depending on who you ask. The northern reaches of Nuna included land that would eventually become North America and Antarctica. And in the south were the cores of South America and Africa. Nuna existed from 1.8 to 1.4 billion years ago, in the middle of the Proterozoic eon. And it's here where we find fossils of the earliest plant-like organisms, red algae, which lived in a shallow sea in what's now India. Nuna broke apart, but the fragments came back together about 100 million years later. This new continent, called Rodinia, was the first supercontinent that geologists had found existed before Pangaea. And geologists were able to reconstruct Rodinia after they noticed that Labrador on Canada's east coast fit quite nicely into the west coast of South America. Rodinia broke apart about 900 million years ago, and shortly after that, the world was plunged into another long ice age. About 650 million years ago, the next supercontinent, called Pangaea, came together. And here the first animals were found in the fossil record, living in coastal waters from the poles to the equator. First came the mysterious Ediacaran fauna, and then the animals that mark the Cambrian explosion. Animals probably didn't live on Pangaea though, because no fossils have been found in terrestrial rocks from that time. But the land wasn't lifeless, it had likely been colonized by pioneering bacteria, algae, and then the fungi. After Pinotia broke up about 550 million years ago, the continents began looking more like the world we recognize. 470 million years ago, in the Ordovician period, the first plants began to live on land. The earliest plant fossils have been found in South America, which was part of the continent of Gondwana. Then, 420 million years ago, in the late Silurian, the first millipedes crawled through the undergrowth on a separate continent just north of Gondwana. And it's known by the catchy portmanteau Euramerica, because it contained parts of both North America and Europe. Euramerica is also where the earliest fossils of insects have been found, about 20 million years later. Then, toward the end of the Devonian period, 365 million years ago, the first amphibians left the swamps to explore the ancient forests that would later form the coal deposits of Europe and North America. And then the earliest amniotes, vertebrates that lay shelled eggs on land, showed up 310 million years ago, right before the formation of the most famous and most recent supercontinent, Pangaea. Pangaea began to form 300 million years ago at the end of the Carboniferous, when North America and Eurasia, together known as Laurasia, collided with Gondwana. And because there were no oceans in their way, animals were free to roam all over Pangaea, which is why similar species are found in areas all over the world in this time. But life there wasn't exactly a picnic. Because Pangaea was so incredibly huge, moisture from the oceans couldn't reach the interior, which made most inland regions pretty much uninhabitable. And of course, making things even less picnicky were two really terrible mass extinctions. First was the Permian Triassic extinction 252 million years ago, aka the Great Dying. It was probably caused by a series of massive volcanic eruptions from fissures in Pangaea in what's now Siberia. These eruptions likely set coal fields on fire and dumped massive amounts of CO2 into the atmosphere and oceans. The super hot air and super acidic rain and seas that followed killed almost everything. 50 million years later, the Triassic came to a close with another mass extinction, wiping out a huge number of crocodile and mammal relatives. This too seems to have been caused by volcanic activity, only this time as North America started to break away from the rest of Pangaea. But among the survivors were the dinosaurs, and as Pangaea broke apart, dinosaurs on different continents became isolated and developed into vastly different forms. The semi-aquatic Spinosaurids, for example, lived on the remnants of Gondwana. Meanwhile, horned dinosaurs like Triceratops mostly lived in North America. Then, after the KPG extinction wiped out the non-avian dinosaurs 66 million years ago, it was mammals' turn. Living on isolated continents like the dinosaurs once did, they too diversified into lots of different and weird forms. Finally, those isolated continents came into contact again in the last 5 to 10 million years, allowing animals to cross new land bridges into new environments, ones we can recognize pretty well today. But of course, things keep moving today just like they always have, at a rate of about 2.5 centimeters a year, in fact. And scientists can predict how the world might look in, say, 50 million years based on how fast the continents are moving and in which direction. So what will future Earth look like? Well, North and South America are both moving west as the Atlantic Ocean continues to grow. Africa is moving north and will collide with Europe, probably forming a huge mountainous plateau, kind of like the Himalayas, where the Mediterranean Sea is now. Australia is also moving north and will eventually smash into the Indonesian archipelago. But beyond the next 50 million years or so, the future becomes harder for us to see. One theory called Pangaea Ultima proposes that a subduction zone will form off the east coast of the Americas, closing off the Atlantic and forming another supercontinent like Pangaea in about 250 million years. Another theory called Amasia supposes that the Atlantic will keep getting bigger and that North America will join Europe and Asia at the North Pole. And a third theory called Novo-Pangaea envisions a future Earth that's similar to Amasia, but with the Pacific Ocean closed off, as Australia and Antarctica move into the former ocean basin. By then, of course, a quarter billion years from now, our descendants and the other descendants of the modern world will have evolved and diversified to occupy a planet that looks totally different. But they'll be along for the same ride that we're on today, as forces deep within the Earth cause our idea of here to slowly drift, just as it has for billions of years. You and I have been through a lot together today, so I appreciate you sticking around for this whole saga of the supercontinents. As always, I want to know what you want to learn about the story of life on Earth, so leave us a comment down below, and if you haven't already, go to youtube.com/eons and subscribe. And if you're like me, and I hope you are, and you're interested in the big picture things, then you should really watch Space Time, a show that answers terrifyingly difficult questions like how big the universe is and what's up with dark energy. Trust me, your brain will thank you.